Hello? Okay, so because of the internet problem, we wasted about more than half an hour. So let us start it anyway, and hope that the internet will not disconnect. We will not be having problem. Okay, so last time uh, we had eigenvalues problem, right? There was a Hermitian operator, and uh, to find its eigenvalue, we will write the eigenvalue equation, right? Then solve the eigenvalue equation in the form of determinant of that matrix is equal to 0, right? And then after solving the determinant problem, or we can say that we said that is the characteristic equation, right? So after solving that characteristic equation, uh, we get the values which we call the eigenvalues. Then putting eigenvalues back in the matrix equation, right? Uh, we get the eigenvectors one by one corresponding to each eigenvalue. That was the eigenvalue problem. Now we go a little, we also did the theorem number 9, and now we do theorem number 10, right? Uh, this theorem states that to every Hermitian operator, right, there exists at least one basis, right, in which the operator is represented in the form of a diagonal matrix. And those, the eigenvectors, sorry, the basis, that basis in which the operator is represented in the form of a diagonal matrix, we say that those are the eigenvalues.
जी सर
बस mun ya lanja gada wada rafa.
نن بتقلار شو سر واسم تيم
Bas kadai zal labya da shi usho no bya bya bas kur te zu asem da garme da rutai waqte.
आओ सर تيم
Oh,
تيم लेट थे सर
template te waso. Template te no ko. Za shuru su ya kana. Oh, let us see. If it is disconnected again, then we should go home. Okay, so I was talking about theorem number 10, right? It says that to every Hermitian operator, remember, Hermitian operator corresponds to an observable. An observable means something measurable, something we measure in our lab, right? So a Hermitian operator actually corresponds to our measurements. So what is the theorem? To every Hermitian operator, there exists at least one basis which consists of its eigenvectors. That basis is made of its eigenvectors. Full basis, full eigenvectors bani basis भी. And then the second part of the theorem is that operator, that Hermitian operator can be represented, right, by a matrix which is composed of the eigenvalues of this operator, and it is diagonal, right? That is the theorem. कोई भी Hermitian matrix, in short, अपने eigenvalues में represent हो सकता है in the form of a matrix, and that matrix will be diagonal in its eigenvalues, right? तो हमारे लिए एक आसान basis भी है, and that basis is the basis of the eigenvectors of the matrix, right? So let us prove this theorem, right? Right? So there is a Hermitian operator, so there should be at least one eigenvalue, or there should be at least one eigenvector corresponding to it, right? Hermitian operator है तो इसकी कोई eigenvalue तो होगी ना, जब आप measure करेंगे तो आपको कुछ तो laboratory में मिल जाएगा. That is called the eigenvalues. So Hermitian operator, and it should have at least one eigenvalue. Let that eigenvalue is omega 1, right? And we can get it by solving the characteristic equation, right? So we always start by, if we want to solve a problem of the eigenvalues of a Hermitian operator, right, or whatever operator it may be, we actually solve its characteristic equation, right? We start from the characteristic equation. So let us start from the characteristic equation, right? Which is determinant of, the characteristic equation is determinant of omega minus omega I is equal to 0, right? So we said this Hermitian operator should have at least one eigenvalue. So let that eigenvalue is omega, right? And corresponding to this eigenvalue, it should have at least one eigenvector. And let us call it this. So it should have one eigenvector, right? And One eigenvalue, one eigenvector. Right? Consider a set of vectors. Consider a set of vectors, blah, 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 1, 2, 3, well, so many. Consider a set of vectors. Remember, what we are proving? We are proving something, a set of eigenvectors, a set of bases. So basis हम क्या होता है? Basis जो है एक set of some quantities होता है. A basis is a set of some quantities which obeys some conditions. You remember those conditions. They should have associative property of addition and commutative properties, and they should obey closure property, all these. So let us consider a set of vectors, right, which are all perpendicular to this vector. Let us consider a set of vector which is all perpendicular to, right, this. One means this one, right? So that is one. We perpendicular and 1 and 2 and perpendicular 1 and 3, so and so on. इसकी एक set हम लेते हैं, and such that all these vectors are perpendicular to this vector, right? So let this operator omega acts on this basis. Let us consider a combination of this vector and this subset. We call it a subset, right? And let this act on it. So we will have a matrix of the form like this. Omega 1, right? And 0, 0, 0, 0, 0, 0, 0, 0. And here should be like the remaining, that will be like something here. This is another, like this will contain all these vectors, all this here. We said actually this is considered, we said the columns of this vector, they represent the eigenvector, right? And this eigenvector of this corresponds to the eigenvalue omega 1, right? Okay. So now, if we consider this as a submatrix, right? We consider this as a submatrix in which this omega is operating, can operate. Right? So for this, if we want to solve the eigenvalue problem, we will write again a characteristic equation, or we can write a characteristic equation, right? And this characteristic equation, like if this, to apply this, determinant of omega minus omega into I, right, is equal to 0, right? So we can write this as like determinant of what? Of this. And that would be omega 1 minus omega right? 0, 0, 0, right? And 0, 0, 0, etc. And that stuff, the remaining box, that is equal to 0, right? So if we want to take the determinant of this equal to 0, so we can expand it with respect to this or with respect to the row or with respect to this column. Suppose we expand it with respect to this, then it will be like omega 1 minus omega, right? And this thing, and determinant of the box, right? Part. Determinant of the box part, right? And we know that this determinant of the box part actually gives us a determinant, gives us a polynomial. So this will be a polynomial, right? We know a determinant gives us, if the characteristic equation is solved, it gives us a polynomial. We know that. Characteristic equation, when we solve it, it gives us a polynomial. Right? So let's write the polynomial in the form m omega to the power m, right? And equal to 0. Suppose the remaining here, the power of this is n. Starts from 0 to n minus 1 because we said there are how many? Like suppose there are n minus 1 sets. Along with this, it becomes n. And suppose this subspace consists of elements up to n minus 1. So it will be like omega 1 minus omega and a polynomial n omega. And the order of the polynomial will be n minus 1. This will be n minus 1. N is just it's a label here, it's label. So it will be after order of n minus 1, right? So that will be equal to 0. Yes? Nothing? Class Jerry. Ini?
Nasa matang kasi salam guru. Basta basta small sa level.
Salam guru ki yo class Jerry.
Nasa.
Okay. So now we will say so again that this polynomial should give at least one root. If this is a polynomial, it should have at least one root. Right? And that root will be, suppose that root of this is omega, 2 is the root. So there is the eigenvalue of this part. This part. Basically, we already are done with this. Omega is equal to omega 1. Look, this will give us what? Omega 1 minus omega is equal to 0. It means omega is equal to omega 1, which we already considered. So it is of no use to us. ये तो हमने पहले भी किया, हमने इधर ये कल, right? इधर की बात है. So this is a polynomial in omega, and it should have at least one root if we want to solve it. Let that root is, we call it omega 2, right? And if this is having a root omega 2 eigenvalue, right? Then it has an eigenvector corresponding to it. And let that eigenvalue corresponding to it is equal to omega 2. And we said, remember, this was the condition here, that these vectors are all perpendicular to this. So W2, omega 2 vector is perpendicular to omega 1. You will say omega 2 vector is perpendicular to omega 1 because ये तो हमने पहले ही consider किया था, suppose किया था हमने that this is perpendicular to that. So now here we can write the situation right further and you know by again this is like omega 1 minus w, here will be omega 2 minus w, and then minus omega, and then we will have another submatrix here for the submatrix, right? We will have omega 1 minus omega, we will have a characteristic equation for this whole situation. Now it will be omega 1 minus omega is equal to and this thing is equal to 0. Now for this it will be omega 1 minus omega and omega 2 minus omega multiplied by this, and that will be n minus 2 now, because 1 is already gone, is equal to 0. So we get another, this is now another equation in which this will be n minus 2, the polynomial. Again we will say it must have at least one solution, at least one root, and with that is omega 3. With that root is omega 3, right? And suppose the corresponding vector is omega 3, right? Look, this is the eigenvalue. This is the eigenvalue. This is the eigenvalue because this is the solution of the eigenvalue problem. This is the solution of the characteristic equation. Therefore, these are the eigenvalues. Right? So, in this way, if we find all the eigenvalues, right? Omega 1, we find all the omegas, they come like this. Omega 1, 0, 0, 0, 0, omega 2, 0, 0, 0, 0, omega 3, and here 0, 0, 0, omega. Okay. We can now write our operator in this form. And this operator is diagonal in the eigenvalues. So if we make a basis, which consists of the vectors which are all the eigenvectors of an operator omega. I suppose we have an operator of an operator omega, right? There exists at least one basis which consists of the eigenvectors. Now we show that these are all, we can write them as the eigenvectors. पहले हमने इसको जनरल वेक्टर्स लिया था, but condition सिर्फ ये थी कि these vectors are actually perpendicular to this, ये condition थी. अब हमने इसको इस तरह लिख लिया, हमने कहा इस v को हम इसकी आइगन वेक्टर में लिख सकते हैं. इस पे हमने इसको we call it like this. We can replace this with this. Similarly, we can write for this. Similarly, you can write for this another. So we can write an operator in the form of a matrix in which all the numbers inside the entries in the matrix are in the diagonal position, and They are the eigenvalues. They are the eigenvalues of. Now, we did not say here that omega 1, omega 2, omega 3 are whatever. We did not say they are not equal. They are equal or not equal. We did not say anything about this. They could be equal. This could be like this. Omega 1 could be equal to omega 2. Right? Omega 1 could be equal to omega 2. Or could be equal to omega 3 as well. या तमाम एक ही value हो सकती है. They all should, or maybe that we are allowed to take all of them, all of the eigenvalues as the same. Right? So this situation will be called degeneracy. If an operator has two or more eigenvalues, identical eigenvalues, we say here degeneracy exists. Degeneracy So if we want to solve a Hermitian problem, the problem of Hermitian operator, it is always easier to write this operator in the form of a diagonal matrix, because in diagonal matrix the calculations become very easy, because everything is zero except the diagonal. So you multiply it with other vectors, it will be very much easier. Solving that matrix equation will be solving a matrix equation corresponding to that operator will become very easy. So it is always, we prefer, if we have problem, we prefer to diagonalize the matrix, to change the matrix to a basis which consists of its eigenvectors. And if a matrix is represented by a basis or in a basis which consists of its eigenvectors, then the matrix can easily be represented in the form of a diagonal matrix. Right? So, suppose degeneracy, right? So if there are two or more identical eigenvalues, of a Hermitian operator. We have a Hermitian operator, and if two or more of the eigenvalues are identical, that situation is called degeneracy. Right? That situation is called degeneracy. So suppose there is a twofold degeneracy. Twofold degeneracy. Right? We have twofold degeneracy for a Hermitian operator. We have been given a Hermitian operator in which the two roots are identical. For example, something like this, right? We have something like this. Omega 0, 0, 0. Suppose it is in identical, sorry, it is in the diagonal form. And omega 0, 0. And here 0, 0. And here we have omega 3 or something like that. Whatever you call it, 0, 0. Omega 4, and so on, right? These two eigenvalues are the same, right? These two eigenvalues are the same. So, there is a twofold degeneracy. There is a twofold degeneracy. So we can write an eigenvalue equation for this operator. Eigenvalue equation for omega. Right? Eigenvalue equation for omega. So omega should operate on corresponding to this. We have an eigenvector omega 1, suppose, and corresponding to this, we have an eigenvector omega 2. Right? So, eigenvalue equation for omega can be written as like this. If omega acts on this, it gives us the eigenvalue omega and back the omega 1. Back that vector will carry the equation number 1. Right? Also, for omega 2 vector, right, we get the same eigenvalue. Right? Right? This is the situation. We have a degeneracy, twofold degeneracy. The eigenvalues are the same for these two situations. Let us write a linear combination of these two vectors, right? These are two vectors. Suppose we write a linear combination of these two vectors, right? So let us multiply this with alpha. We get omega 1 and multiply this with some scalar beta. Omega 2. This is the linear combination of these two. These are two vectors. So suppose we write a linear combination of them. Like one is this vector, one is this vector, right? Suppose these are two vectors. Omega 1, suppose this is omega 2. A linear combination of them will be something like this. Something like this. This will be a linear combination of this. Omega 1 plus omega. This is a linear combination of them. If these vectors are acting in a plane because they are perpendicular to each other. They are perpendicular to each other, so they form a plane, a two-dimensional basis, which is the plane. And there is a linear combination. अगर हम इसको किसी स्केलर से ज़रब दे दें, so it will become alpha and it will become, वो क्या करेगा? It will either shorten this vector or will make it longer. So, not a big problem. So, a linear combination of these two vectors, we want to see if this is also the eigenvector or not. Right? So let us apply the operator omega on a linear combination of these two vectors, right? Alpha, omega, omega 1 plus beta, omega, omega 2. Let us apply omega on the linear combination of these two vectors. इस पे हम अप्लाई करेंगे, लेकिन इस पे अप्लाई करेंगे क्या होता है, ये हमारे पास आइगन वेक्टर आता है कि नहीं. So it will be like this, right? Omega, right, acting on this alpha, omega, omega 1, right, plus omega, right, beta, omega, omega 2, right? So these are constants, some scalar constant. So इसको हम बाहर लिखते हैं, right? No. A linear combination, sorry. A linear combination of these two vectors. Where are the two vectors? These are the two vectors. So, not omega. A linear combination of these two vectors. So there is no omega here. Just two vectors. A linear combination of these two vectors will be like this. And suppose we multiply them with some alpha and some beta, that will be a linear combination. Right? So that would be omega 1 plus beta, right? And to omega 2. Now we know that, look, we started from here, right? It will be alpha, here it will be omega 1 plus, here it will be beta, and when this acts on this, we get omega and omega 2, right? Or we can write this as omega alpha, omega 1 plus beta and omega 2. So look, here we say this is the eigenvector of this operator with eigenvalue omega. This is an eigenvector of this operator, the same operator, with eigenvalue omega. We say this is here is a twofold degeneracy. So when we apply this, the operator to a linear combination, this one, a linear combination of these two vectors, we also got the eigenvalue. So in the linear combination, it is giving us the same eigenvalue. So what we get from here, again, first listen from this the degeneracy. If there is a degeneracy, whatever is the number of degeneracy, the same is the dimension of subspace that we can get. For example, you have twofold degeneracy here. There are two identical values. And therefore, this means that you have a basis which consists of two perpendicular vectors. This is a two-dimensional basis. It is a plane. तो जितनी हमारे पास डिजेनरेसी होगी उतनी ही हमारे पास उतनी डायमेंशन की हमारे पास स्पेस एक सब स्पेस आ सकती है. We will have a subspace corresponding to that degeneracy. A subspace of the whole space of the whole space of the operator. Now, there is another lesson here, right? Look, if this is equation 1, this is equation 2, this is equation number 3. So look, alpha and beta are just arbitrary. You can take alpha as whatever, you can take beta as whatever. They are not constant. Alpha and beta are not constant. कोई भी कुछ भी हो सकता है इसमें. आप कोई भी number की जगह पुट कर सकते हैं. So this combination can be of any type. It means that we have an infinite number of choice to select these two vectors such that the resultant will satisfy this equation. तो इसका मतलब ये है ना, इस तरह भी हो सकता है. Look, you can have this system, or you can have, because you can multiply with alpha, this multiply this with beta, provided they satisfy the equation. So you can have another pair like this, and this pair will also satisfy this equation, because it's just a scalar multiplication with these two, right? Similarly, you can have another basis. Similarly, you can have another basis of these two vectors, and so on. You have within the two-dimensional plane, you have an infinite choices to select any one from them. You have a freedom, right? This is only a rotation, So for degeneracy, we have another freedom. And the freedom is you have infinite number of choices and you can just select any two from them, provided these two vectors are perpendicular to each other. And you will not be violating any rules, or you will not be creating any problem. So you have a freedom. So ये आपके पास within the subspace, within the degeneracy, within the subspace आपके पास दो numbers आप को करें, आप दो numbers का कोई vector बनाएं, right? Such that they are perpendicular to each other. कोई भी शक्ल हो इनकी, plane में, एक plane में वो किसी. So you can, within a subspace, you can rotate your bases within a subspace. Within a subspace, you can easily rotate your bases. Right? Or within the subspace for degeneracy, within a subspace, you can rotate your bases, right? With no problem. You can rotate your base. Let us do an example. You will understand the situation after we solve the problem. Another problem, an example. Right? Example 1.8.5. Right? We have been given an operator. Right? And this operator is what? 1, 0, 1, 0, 2, 0, 1, 0, 1. Right? This is a three-dimensional matrix. Three-dimensional matrix. Right? And we are asked to find the eigenvalues. Eigenvalues and eigenvectors. So the first thing is, first thing is we find the characteristic equation of this operator, because we are going to find the eigenvalues, right? So characteristic equation of this operator will be is equal to determinant of, it was like this, determinant of omega minus omega I is equal to 0, right? And it will be 1, right? Minus omega, right? 0, right? And 1, 0, and here 2 minus omega. This is the identity operator. Identity operator is something like this: 1, 1, 1, 0, 0, 0, 0, 0, 0. So if you put this here, then you will have subtracted from this, so you get this thing. And 0, right? And 1, 0, 1, minus omega. So minus omega. That will be equal to, right? Now I expand it with respect to this row, this column, or this row. किसी भी column or row के साथ इसको expand करें, right? So you will get what? 1 minus omega. If you want to expand it with this is gone, this is gone, right? Then you will get this thing: 2 minus omega, 1 minus omega. Right? That is equal to n plus, now this one. So this is gone, this is gone. So what we are left with plus 2 minus omega multiplied by 1. So this is equal to 0, right? Oh, let us take 2 minus omega term. So that will be 2 minus omega, and I will get here 1 minus omega squared, 1 minus omega whole squared, right? and minus or plus. Oh, look here. This is plus 1, right? So with respect to this now, so this goes and this goes, and this. So this is plus, but this is minus. So here will be a minus for this. A minus for this. And this minus will become here, multiplication of this will be minus. So that will be, okay, I have already taken this a's common, right? So this will be 1 here, minus 1 is equal to, clear, right? This is clear, see? Okay. Expansion of determinant. Okay. So it will be, what we will get, it will be like, I took this common from here, this, so we got this, right? So it would be 2 minus omega, right? And that will be omega squared minus 2 omega equal to 0, right? So we have here the results we have is omega is equal to 2, right? Here, from here, I can take omega is equal to common, right? And that omega will be equal to 0. And here, omega minus 2. So again, we will have omega is equal to, there are 3 roots. Omega is equal to 2. Let's say omega common then that omega will be equal to 0. And the remaining is omega minus 2. So omega is equal to 2. So we have twofold degeneracy. Twofold degeneracy. Now we want to find the eigenvalue. So we got 2 eigenvalues, right? We got these eigenvalues, right, by solving the characteristic equation. So these two, there is a double degeneracy, twofold degeneracy. Now let us find this first. So it would be like you put them back into that equation, right? The matrix equation. It was like that, right? So bar omega is equal to 0. What is the eigenvectors for that? So we put them in back in the matrix equation, right? It was like this: omega I j minus omega and to delta I j, and it was j start from 1 goes to, j will start from, okay, and v j is equal to 0. It's a three-dimensional problem, right? So we will have a matrix. With, omega is three-dimensional matrix. So we will have the matrix equation, something like that. Right? 1, 0, 1, and 0. 2, right? 0 and 1, 0, 1. And V1, V2, V3, and is equal to 0, 0, 0. Look, omega ij. So omega 1, 1. Omega 1, 1 is this 1. And here we say minus omega 1, 1. Minus omega 1, 1 will be minus omega. But omega is equal to 0. So here again, for the second one, right? We will have all 0 except I and j are equal. So again here, omega 2, 2. So that is omega 2, 2 equals 2 minus omega and this. So minus omega, omega is equal to 0. For the third one, right? Omega 1, 1, omega 1, 3 is this. No, 3, 1. Omega 3, 1, 1. And this will be 0 because of this. And then this one is already 0. And this is also 0 because of I is not equal to j. Here, there is 1. Omega is 1 here. And this thing I and j, that will be 1. But omega is equal to 0. So it will be like this: 1, 0, 1, 0, 2, 0, 1, 0, 1, and V1, V2, V3 is equal to 0, 0, 0. Right? So let me expand it. So solve this matrix equation. V1 plus V3 is equal to 0. Right? Here, this with this 2v2 is equal to 0. Here this again, v1 plus v3 is equal to 0. v1 plus this with this, right? यहाँ से 701 we get only one result from here, right? यहाँ हमारे पास सिर्फ एक ही मतलब की चीज निकलती है. We get only one information from here. You can say two information. Two informations are two pieces of information. Two pieces of information, right? One is like V2 equal to 0. V2 equal to 0. Or you will say V1 is equal to minus V3. V1 is equal to minus V3. Our SRY is going, this is not giving an extra information to us. The same thing. But the next is V2 equal to 0. So we have only one thing. Our vector can be like this. 0 could be like this, right? V1, V2, V3. So it would be like something like that. V1, we put V1 for V1. For V2, we put 0. For V3, we put what? Minus V1. Right? We have this equation. Right? We know this thing, but we don't know V1. For this, let us apply the normalization condition. Right? To know Asim, Asim,
जी सर
कम से पूरे तासो आवरे दो दता ताऊ जिते पूरे आवरे दो
نه سر دغه پاتې شو
कम
د
से दता
نارملایزیشن کنډیشن سر
दा
دغه
दा
ځینې
दिने
دغه ځینې به شروع کوو
दा ताऊ जिते पूरे तासो दले
بالکل سر دا
हाँ
نارملایزیشن کنډیشن به اپلای کوو سر دغه سټپ دی
दा
بیا کټ شو سر
Asim, can you listen to me? Asim, you can hear me? Asim, anybody can hear me? Anybody can hear me? Are you hearing me?
It's not clear.
Anybody can hear me?
Sir, voice is not clear and picture as well.
Oh, well, you can hear me now, right? Anybody hear me?
Sir, it's not clear.
Okay, I'm recording, so let us apply the normalization condition.
Also, आवाज कट की sir.
So the normalization condition, trying to multiply the product into one, so that is a job office. This is a normal multiply you multiply with one plus is equal to one is equal to 2. So we want to now zero is equal to that. So you get you take comma, and that will be 1 0, 1. So you get what value? You get this factor. You got this. Yeah, you got that. Now, let us think about that. Okay, so now the next one is corresponding to the degeneracy. Degeneracy, right? W is equal to, yeah, omega is equal to 2. So, this is the degeneracy, right? Again, we saw the matrix solution, right? It's the same thing. Again, putting omega is equal to 2 in the matrix equation. When we put in the matrix equation and solve it, what we get is minus V1 plus V3 equal to 0. And this is like 0 is equal to 0, and the third is V1 minus V2 equal to 0. So here, V1 is equal to V3. V1 is equal to V3. 0 is equal to 0. V1 is equal to V2. Look, this is arbitrary. This is a case of double degeneracy. This is a good example. So what we have would be like something like this. Corresponding to W is equal to W is equal to 2. What is the vector corresponding to this? So we put value back and we got what? We got V1 is equal to VC. So it will be like this. 2 will be like this. V1 is equal to VC. Here again, in order. So let's That was good, actually. Well, about the solve which is a problem for us to do. Okay, so we have this V1 is equal to V3 and that is equal to V, everything we have like that. Just the V1 will equal just the V1 will equal, because this is equal to this. This is also equal to V1, this is also. So we have this thing. Okay, this, right? So now let us normalize it and get something from here, right? Normalize. So it will be like this 2 and 2 is equal to 1 normalized case, huh? So it will be like this V1 star, V1 star, V1 star, and V1, 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 and that is equal to 1, right? And here it will be V1 square plus V1 square plus V1 square is equal to 1. And here it will be, right? So it will be 3 V1 square equal to 1. Our V1 square will be equal to 1 over 3. Our V1 will be equal to 1 over 3 square root. Right? So, what will be the vector for the degeneracy? Right? Look, we put this V1 is equal to 2, 1 over 2 square root, no, 1 over 3 square root, Mara. 1 over 3 square root. 1 over 3 square root, we put it here, V1 is equal to that. So 2 will be equal to, right? 1 over 3 square root, 1 over 3 square root, and 1 over 3 square root. So that would be equal to 1 over 3 square root and 1, 1, 1. That is your one vector. That would be the full equation word. Number is 2, right? Okay. Now for the other one, right? We cannot get anything more from here, right? That is one. We will have the same thing. Omega is equal to 2, we will get the same thing. How we get our next equation. So the condition is that it should be orthogonal to this one, to omega 1. If we want to find, we have the condition that should be orthogonal to omega to 2. Is basis में हमारे पास again we our eigenvalue is again W is equal to 2. So the same process we will solve. We will have the same procedure because omega is equal to 2. We get nothing from this. Again we will get this thing. But we can apply a condition on it that vector for 2, इसको मैं second कहूँगा. Second. 2 second. ये first हो गया है, उसका second. So this should be perpendicular to 2. This should be orthogonal to you. अगर हमारे पास basis बनाते हैं और we know that they are all perpendicular to each other inside the basis. So let us apply that. When this is perpendicular, right? So, yeah, okay, let me write that there. So, 2 second should be perpendicular to this. It will be equal to 0. Right? हमारे पास V1 was equal to V3 in the first case, right? And the second was V1 is equal to V2. So we take this as a choice or whatever. We take it as a choice. So if one vector is this thing, we can say, let us change it. Let us call it, make it different. So we make it different. Could be like that. The 2 is, okay, so make it like that. Right. Determinant is equal to 2 and second. That is supposed like this. 1, 1, V2. Right? Now what was here? Here it is 1 over 3 square root. So I will write 1 over 3 square root here. Right? 1 over 3 square root here. And I will write this in the form of the same column 1, 1, 1. I will write this in the form of a broad, which will be like this. ये मैंने इसको select किया है. So it will be like 1, right? V2 and this should be equal to 0, right? Okay, this will be 1, right? That will be V2, no, 1 plus V2 plus 1. So 2 plus V2, that is equal to 0, right? And is equal to 0. So you would multiply it with 3 square root, so ये चला जाएगा, and because V2 is equal to 1. V2 is equal to 1. So I can write it like this. The second one is W is equal to 2. The second one, that would be equal to 1, right? Minus 2 and 1, right? Now, let us normalize it. Right? We can write it like that. A, right? And to this vector, should I write second and the first, the 2, that is equal to 1, right? So I will write this in the broad form with A squared, because A here. So it will be like this. Well, that's done. Okay. This is the one will check that. Again, let's see what check. We will check it later. You should check it, but there is some something bugging. But since we are getting late, so later on you can check it, and I will check it too. So let us write it simply. So we'll be like, I can write it like that. For this, I'm writing A. Suppose I don't know it. Then and A for this. So is clear. And for this, I write it 1, 1, 1. And for this, I write it 1 minus 2 and 1. All right? And that is equal to 1. So, what here would like is here, and that would be 1 plus, right? Oh, خبري غلطي में उपरा कमांड मंडयम गलती में उपरा खास लाजम से लगे जुड़ा ना मलादेश को खलक को लजान सला कि बस स्केल ऑफ प्रोडक्ट फॉलो ना मलादेश में वो लाइक को लजान सला ना so I will write it like that और खत्म so no, suppose gamma A because I don't know what is the magnitude of this factor. So that's here. Now let's go. Now let's go. Double AC or double C second or double AC or double C second, right? And that will be equal to 1. So E square, that is an A, A square. Or double reverse will become second, or second, that is equal to 1, right? A square, the second, so that's ulta ka mudasi barashi, 1 minus 2, 1 barashi, or now the column form will become 1 minus 2, 1 barashi, that will be equal to 1. Now it's here, right? And 1 to 1. -2 plus 4. 1, 1 plus 1 is equal to 1, right? And that will be equal to 6 A square is equal to 1. Or this implies that A is equal to 1 over 6 square root. So now the vector is, now the second is equal to, the second vector corresponding to W is equal to 2. The second will be equal to, for A, I will write 1 over 6 square root, and then will be 1 minus 2 and 1. So, for the delta degeneracy when omega is equal to 2, we get this factor and we get this factor. One is this, one is this. And you can prove that they will be perpendicular to each other. And if you take a dot product of the two, that will be equal to 0. Because they must be perpendicular to each other inside the basis. And we will discuss this in our next class too. I will have a review on this, and there are some consequences of this that we will discuss them again. Today was not a good experience because of so many problems in the internet. Hope that in the future we will not have the same problem. So see you, and tomorrow we will not have a class. Thank you just for listening to me. Thank you so much. Tomorrow we will not have a class.